Good morning, everyone. It's always nice to see some new participants compared to the previous webinars of the project. So my name is Maria Rodriguez, and this webinar today belongs to this project called i4Driving, Integrated 4D Driver Modeling Under Uncertainty. Next slide. And this is an European project. It's a research project that started in 2022, and we are finalizing it end of this month. So we are now almost reaching our final event series of webinars. So you can see our partners on the right side. And next slide. The overall objective of this project is to deliver this library of credible models of heterogeneous human behavior. And these models will help basically to serve a standardized multi-objective evaluation framework adaptable to applications. And today we will focus on these applications. I will tell you more in a little bit. This is generally how the project is organized. So we started by gathering evidence from human factors from data, and then we started developing the i4Driving model, and we had simulators and test experiments that helped to validate and calibrate the model. And we are now in this phase, which is the last part that you see on the right side, of showing how the model of i4Driving works in the different application cases that we will present today. There's only one final event last, so the last one will be on the 31st of March. In the QR code, you can still register for that one. And today, next slide, we have the webinar number 7, which is exactly showing these target applications. So we will have 4 speakers. We have Emil from Warwick. We have Federico representing RDW, Christopher from ZF, and Athina from Aimsun. And without losing any more time, because I know that it's a packed exercise that we will have to do to present as much as possible from the many findings that we had. So Emil, please, you can start.
Hi everyone, thank you Maria for this kind introduction. So as Maria said, today me and partners from RDW, ZF and Aimsun, we will present the overview of evaluation in target applications. So let's start. The agenda for this webinar is, I will start with the introduction. I will present the scenario-based evaluation workflow. Then we will see how we define the core scenarios and which simulation environments we're using in the applications. After this general overview, we will dive into individual application and results of those applications. So let's start. Introduction. So the same slide as Maria showed. Just want to remind that probably if you had a chance to join the previous webinar, you've seen that colleagues concentrate on the collecting the requirements for the model development, developing the model itself, collecting the human factors data, and calibrating and validating the model. This webinar is about application phase, so we can think about this as a use cases phase. So we take the model and we want to demonstrate that it can be deployed around 5 different real-world meaningful applications. And the reason why we want to do this is we believe that currently there is lack of credible human driver baseline that can be used in the virtual simulation for assessment of automated driving system and ADAS systems. Each application is led by the domain expert. We start from the human driver baseline for prospective effectiveness assessment of road safety peers, and it's led by the WMG University of Warwick. The second application is human driver baseline in consumer testing campaign of ADS, and it's led by the Netherlands Vehicle Authority, RDW. The next application is applying the model in the mixed traffic simulation, which is led by the Aimsun. Next, we have model used in the safety, traffic, and energy efficiency assessment in mixed traffic, and this application is led by ZF. And finally, we have human driver baseline for insurance qualification schema, and this application is led by the Swiss Re. The scope of this application phase is split into two main elements. The first one, as I said, we want to demonstrate that the model can be deployed across those 5 different applications. And the second one is we want to develop the methodology, so common evaluation workflow, to evaluate the performance of ADS and ADAS. And also we want to do this, we want to develop the toolchain and tools that are required to make such an evaluation. Um, Obviously, I think the also secondary outcome of our exercises is the whole consortium wants to see how the model behaves in the actual applications. Does it behave realistically? Does it behave similar to what human will behave? And can we see the difference in behaviors as we would expect from the human? So let's start. As I said, within the scope, the one element was to define the scenario-based evaluation workflow, and this work was already summarized in deliverable 6.1. So you can all access this document already. It was a while ago, but in summary, we came up with this scenario-based testing workflow, which concentrate on 3 main elements. In summary, scenario-based testing workflow concentrate on the edge cases, not on the distance-based method, which is not feasible to do for the ADS assessment. So at a high level, this workflow contain 3 main elements, which is the scenario. Scenario means it's the real-world road situations in which the system can be placed and tested. Those are the edge cases, so challenging situations for the system. Next, we want to execute those scenarios in environments, and environment can range from the purely simulation-based, virtual simulation-based, to the track-based and road testing. And finally, the results from this execution, we want to analyze and create some arguments in certification, safety, evidence, and argument step. So those are the main elements. If you look on the functional steps, more concrete steps, first we need to define scenarios. We need to came up with what kind of scenarios do we need. Secondly, we need to format those scenarios in some simulation readable common format. Then we need to store it in some database, and then we can move to the test allocation. So we allocate those scenarios across different simulation environments, and we execute them and analyze. If if we see from the analysis stage that it is not enough, we need to come back to the scenario creation and execution of the scenarios. So that's high-level workflow. But as I said, this was already delivered a while ago, and recently we realized that there are some other initiative in the CCAM community, which is the Sunrise project, which is actually working on the harmonized safety assurance framework, which you can see that the workflow and steps are very much similar, but it's just more advanced. So when I say advanced, you can see that there is a bit more thoughts put in the process, and we can see that we have an input, which is the operational design domain, and behavior competency input to the workflow. So this is the boundary in which the system is designed to operate safely, and the complete testing should be conducted within this boundary. And we also have audit. We have a bit more around the safety argument, which is we added the coverage, so saying whether the testing is enough or not. Um, uh, so we, at this point, we realized that I think aligning our approach with safety assurance framework from SAF will be something that we should do it. So now we can dive into how we define the core scenarios. So the objective of this task was we look on the we define high-level scenarios that can be deployed across different applications. So all applications can use those scenarios for the evaluation. So this is the high-level overview of the scenarios, and we look on the three different sources. We firstly look on the use cases which were summarized in the deliverable 1.6 of the i4Driving project. And we looked on the Euro NCAP specification, and we also looked on the LKS UN R157 regulation. And we came up with 4 different scenarios. The first one is jaywalking pedestrian. The second one is lead vehicle following. So ego is following the lead vehicle, and lead vehicle is slowing down on motorway. And then we have cut-in, so the agent is cutting in front of ego. And then we have approaching cyclists. So on the crossroad, the cyclist is approaching the ego from the back right side of the ego. So across those schematics, you can see that the blue vehicle is ego, yellow are fixed agents, and the red one is pedestrian jaywalking the road. And now I will just give you a bit of overview of what simulation environments we used for our applications. We have 3 main simulation environments. And the first one is Aimsun Next for the traffic simulation. We have WMG simulation and DSpace simulation. And at this point, we all had our specific simulation environments, but the question was how we can execute the i4Driving model in those environments. So the one way was to natively embed the model in the simulation platform, and this route was followed by the Aimsun. So Aimsun natively programmatically embed the model in the simulation software. But the second way was to come up with some sort of cost simulation bridge. And between WMG and TU Delft and ZF, we came up with this socket-based, message-based cost simulation bridge, in which we can, on one side, we can have the i4Driving model, and on the second side we can have any external simulation environment. So it's not only applicable to the DSpace and WMG simulation, but we can, by using this bridge, we can link any external simulation environment. So as I said, on the left side you can see is the i4Driving models, which are hosted in Open Traffic Simulation. And we have bidirectional bridge with the external simulation environment. So this is one outcome of tangible toolchain of our work. And probably you will see all the documentation somewhere on the OTS website. Okay, that was the overview of what we have mutual across the applications, and now I will dive into the first application, which is the safety effectiveness Peers application. So Peers was established in 2012 and was consisting of open consortium of automotive industry and research institutes and academia. And they all met with the overall goal to harmonize the prospective effectiveness assessment of active safety system by simulation. And the second goal was to encourage this discussion on the safety performance assessment by the virtual simulation mean. And the tangible result of this initiative was the ISO 21934, part 1 and part 2 as well. In the part 2, there was a guideline and the requirements for applications for the prospective safety performance assessment of pre-crash technology by virtual simulation. So that's a tangible result documented in this standard. But at the high level, this document was mentioning how we define the scenarios and how we use the simulation, how we allocate those scenarios within the simulation, and also how we analyze the result and how we can get some safety conclusion from those simulation result. So we believe that the peers methodology at the practical level can be addressed by the previously defined common evaluation workflow in deliverable 6.1 and further aligned with the Sunrise SAF workflow. And this is the evaluation methodology that in peers application we decided to use. And now if we have a look on the more concrete lower level steps, what we're actually doing on the very concrete steps is we need to have concrete scenarios in some simulation readable format. First, we execute those scenarios with the i4Driving model. So the model is placed in this situation. We simulate this in our virtual environment. We get the simulation data. We pass this simulation data by safety matrix, and then we can draw the conclusion. And this is treated as the human baseline. Next, we use exactly the same concrete scenarios. So we place the generic ADS model in exactly the same scenarios. We get the simulation data. We pass by exactly the same safety matrix, and we evaluate and get the result, and we can compare this to our human baseline. So previously defined core scenarios, we now make it more peer specific, more safety critical specific, because this is the safety application. We want to make it safety critical specific scenarios. And to concretize those scenarios, we need to decide on what kind of format we want to use. And we decide to use ASM OpenX type of format. And on the left side, you can see we have ASM OpenDrive to describe the static road network description. And we have ASM Open Scenario, which describe the dynamic scenario description. And together, we have complete scenario description with dynamic and static content. And this is the example of the first scenario, how we concretize this scenario. We decide to have two different types, type A and type B. In type A, we just have simple pedestrian crossing the road and ego acting to this jaywalking. In type B, we decide to have some occlusion in front of ego, so and also add the following agent, so the ego will have a bit more challenging situation to be in. And we follow the simple sampling method of parameters. So we decide which parameters we want to sample. And in this particular scenario, we decide to sample initial speed of ego, the speed of pedestrian, what's the speed of pedestrian crossing the road, and what's the triggering point of when pedestrian starts crossing the road, and this is based on the time to collision. So yeah, we came up with a few different values in ranges 30 to 70 kilometers per hour. 5:10 for the pedestrian, and time to collision 1.5 and 3 seconds. The second scenario we concretize in exactly the same way. So we have 3 different parameters. The first one is speed of ego, uh, acceleration of the lead vehicle. It's actually deceleration of a lead vehicle, so how quickly the lead vehicle will slow down, and relative initial speed between lead and ego. So is ego following the same speed as lead, or perhaps is going a bit faster? And we've decided to go with some motorway type of speeds, which is 110 kilometers per hour or 130 kilometers per hour, and 2 different deceleration rates, which is 3 meter per second square or 5 meter per second square. The third one is the cut-in scenario. So again, we have 2 different types. One type is we have just lead agent cutting in front of ego. We have ego on the middle lane, and we have a following agent. The B type is we just adding a bit of surrounding traffic just to make the situation a bit more critical. And we sample 3 different parameters, which is the initial speed of ego, lateral acceleration of the cut-in vehicle, so how quickly the lead vehicle cuts in, and time to collision, the triggering time to collision. And again, we use the motorway type of parameters, so 90 kilometers per hour, 120, and 1.5 and 3 meter per second square deceleration. The fourth one was the crossroads scenario. So in this case, we have only one type, the standard type, where the cyclist is just approaching from behind the ego, and ego is turning right on the crossroad where we have the conflict point. And for this one, we decided to have 2 different parameters to sample, which is the initial speed of ego and cyclist initial speed. And we have a few different urban type of speeds, so 20, 40, 50 kilometers per hour for the ego, and for the cyclist is between 10 to 25 kilometers per hour. And then we execute those scenarios using, as I said, using the cost simulation bridge between WMG simulation and open traffic simulation. So on the left side, you can see the GUI from the OTS, and on the right side, you can see the illustration of WMG simulation execution. You might be wondering how we developed the environment. In WMG simulation, we have an option to auto-generate the scenery based on the Assam OpenDrive description. So purely based on the description, we can auto-generate the quite high fidelity scenery. And now, what safety matrix did we decide to use? We decided to go with 4 different matrix. The first one is binary collision occurrence, whether it happened or not. The second one is time to collision. The third one is deceleration rate to avoid collision. And the fifth one is the impact speed. So if the collision occurred, what was the speed on the impact point? And the result, because the time is very limited, I will just present a result for one scenario, which is the scenario 3, cut in. You can see on this plot, the green color is describing the safe cases. So the cases where it was safe. The yellow color describe the near miss cases. So the cases where there was no collision, but it was very close, and the red color described the collision. So you can see on the top row, we have the result for the ADS, for the generic ADS system, and then we have 3 different drivers from the i4Driving model library. So for our execution, we selected 3 different representative drivers just to demonstrate the methodology. So we can see that the results from the drivers in some cases are a bit different, which is actually a good point because we can see that between those drivers there are some differences. They're not all the same. And on the lower table you can see we add scenario ID, so what ID, what parameter is describing. So for this one we can see that, for example, 3.6 all of the drivers and also ADS collided, so it was very critical scenario. And 3.6 we can see that it described the speed of ego 120 kilometers per hour, and the 1.5 time to collision triggering point, so very strict, and 20 meter per second square lateral acceleration. Now, if we look on the safety matrix 2 and 3, which is TTC and DRAC, you can see 2 different plots. On the left one is the result for the TTC. So the blue point, it describes the human drivers. It's the mean result. So this is our baseline. And the orange dot is the ADS. The red zones are describing the critical zone in which there is still a chance that the system did not collide, but it's a near miss. It's a near miss. And on the right side, you can see the maximum DRAC. So what DRAC value we observed, what maximum DRAC value we observed in each execution. It's worth to mention that DRAC unit matrix is only meaningful when the ego vehicle is getting close to any other vehicle. So if they're going away, the DRAC number will be infinite, and there's no meaning in this case. Yeah, I will not dive into analyzing, but all these results will be in the deliverable, Pierce deliverable, which will be shared. And this is the result for the last safety matrix, which is the impact speed. So we can see the orange bar describing mean impact speed, and the red bar is describing maximum impact speed that occurred for this specific driver type. So we can see some differences between the drivers, which again is quite good to see that the drivers behaved slightly different. But for this particular scenario, we observed very high collision speed, which yeah, at the end, it's not a strong safety argument. But in summary, in the Pierce application, we reached both objectives. We demonstrate the application of the model for Pierce, and we also define the evaluation workflow together with toolchain to enable this evaluation. Findings are illustrative, so it's just to illustrate the methodology. We select only handful set of drivers. No definitive ADS safety conclusion we can draw from this work, but this was also not a scope of this work. The outcomes aim to inspire stakeholders in applying the methodology and the human driver models at scale. And that was all from my side. So now I will hand over to Federico Scari from Netherlands Vehicle Authority, RDW. Thank you very much.
Hi, everyone. Thanks, Emil. Let me share my screen too. Okay. So yeah, thanks, Emil. Now we're looking to the second application, namely the one to consumer testing campaigns. So first of all, what are consumer testing campaigns? These are structured programs that evaluate the vehicle that are already in the market for their safety, efficiency, and usability. They do so by providing unbiased safety data on the cars that are sold to consumers. They compare vehicles across different brands under equal conditions. One of their objectives is to encourage manufacturers to improve their safety standards. They do so because the second objective is to publish the results so that we as buyers can make informed decisions when buying a car. In Europe, we have the Euro NCAP, which is famous for their crash test with dummies. And Euro NCAP already covers adult occupant protection as well as child occupant protection. They also look into crash with vulnerable road users, such as cyclists and pedestrians. And they also evaluate driver assistance systems. At the end, they give an overall safety rating, which is given by stars. So the question is, how do we apply and how do we use the i4Driving model to evaluate ADS and ADAS functions? So to answer this question, we divided our task in two activities. The first one, we have the i4Driving model and the open source ADS model running in these three scenarios that Emil already explained. Then we were able to grade the models based on the grading system we developed throughout the project. And so we were finally able to compare the ADS to the driver baseline. For the second activity, we have, again, the i4Driving model and the driving model with an ADAS function. In this case, we went for the autonomous emergency braking system, and we let it run in the pedestrian scenario explained before. Again, we can run the models, grade them, and then we are able to compare them. As already mentioned, the scenarios are based on safety protocols and the UN, as well as our metrics. Specifically for these two scenarios, we based it on the UN regulation, where they developed a difficulty index, which is basically telling us how difficult a scenario is for the vehicles under test. This difficulty index is based on the time headway, the velocity of the agents, also the ego vehicle, and their deceleration and acceleration profiles. So we were able to use their tools to see how difficult our scenarios were. Here we see an example. The markers with the black circle are the concrete scenarios we went for. And we based our evaluation metrics on collision avoidance, deceleration comfort, which is also expressed in the regulation. They have a deceleration threshold of -4 meters per square second as maximum comfortable deceleration. And then the safety distance, which is a distance after the vehicles perform the braking maneuver between the ego vehicle and the lead vehicle that should be at least 2 meters distance. And of course, the scores are then weighted based on their difficulty index, because doing well in an easy condition is easier than doing well in a difficult condition, for example. So results for these scenarios are this one. So both models didn't do really great in this scenario, but it's very important to mention once again that the difficulty was very hard in this scenario. As you can see here, the ADS did slightly better by avoiding 3 collisions. In the next scenario, we also computed the difficulty index. We have here more easy condition compared to before. And our evaluation is based again on collision avoidance and on exceeded deceleration. So we computed the needed deceleration for the vehicle to avoid the collision. If the vehicle was decelerating more, then it was penalized. And again, of course, the score were weighted based on the difficulty index. The results here show a better picture for the models. Both scored better. The ADS avoided all collisions, but it got penalized because of this comfort metrics about the deceleration. The next scenarios are based on the Euro safety protocols. Let's start with the cyclist one. Here they based it on collision avoidance, and so did we. And the results show that the i4Driving model actually performed better than the ADS. With further analysis, we saw that the i4Driving model was slowing down while entering the intersection already, and then either letting go the cyclist or crossing before it, while the ADS failed to do so at high velocities. For the last scenario here, we are evaluating the ADAS function. The Euro NCAP based their evaluation metrics on collision avoidance, and if a collision takes place, then they look at how much the system can reduce the impact velocity. Here we focused mainly on 3 initial parameters, so 30, 50, and 80 kilometers per hour as a urban setting. And the pedestrian was running in front of the vehicle with a velocity of 8 kilometers per hour. The results here are also very interesting. They show that the human model without any ADAS function collided 8 times out of 18, while with the ADAS system on, the system was able to avoid the collision all the time. And this already tells us that the performance of the ADAS function is quite good. It works very well. But it also shows us that in 10 conditions, it got triggered, although the driver would have been able to avoid the collision. Which, with further analysis, we saw that the pedestrian was already sometimes already braking quite hardly. So the fact that the AB kicked in didn't change that much. But in other, we saw that the driver was able to avoid the collision with a slower deceleration, and then the AB kicked in anyway. And this can be not very comfortable for the driver, can also undermine its trust towards such systems. And this highlights the fact that when we such a system to a driver baseline, then we can also point out that we have to tweak the sensitivity of these functions. So finally, what are the main takeaways of our application? Well, we saw that including human models in evaluation is of paramount importance. It gives us the opportunity to see two main advantages. So the first one was to contextualize the results. So if the ADS was performing poorly, we could also check if the human driver how he would have performed. And if the driver would also perform poorly, that we could basically see if the scenario was inherently difficult, or to see if the controller had specific weaknesses that had to be addressed. The second one, if the human was performing better than the ADS, then we could point out with further analysis towards specific behaviors that the ADS should improve. In this case, safety is #1 priority for our grading, as it should be. But we also realize that comfort is and does play a big role in such grading, especially for us and consumers that have to make informed decisions when buying a car. Because comfort can also influence our use and trust and acceptance of such systems. Simulation evaluation is also very important, as we saw, because it enables us to evaluate safety critical scenarios that in real life would have been almost impossible to perform or very dangerous. And also to look at edge cases that we were not able to get from fleet data, for example. Simulation also enables us to reproduce any safety critical scenarios as many times as we want, and also to create an infinite amount of safety critical scenarios. Of course, simulation have some limitations, and that's why we see simulation evaluation as parallel to real-world test and real-world data, not to replace it. That's it, and the floor is yours, Christopher.
Okay, then I will directly continue. So application number 3, the task ZF has focused on was to cover both aspects, safety and the efficiency aspect. Maybe as an introduction for you, if you want to analyze a system under test that covers both aspects, safety and efficiency, and that interacts with the traffic, you need an appropriate testing strategy. So focusing on the safety aspect, as Emil already mentioned, the scenario-based testing approach has come to the forefront, which basically focuses on small-scale simulations. In general, it's about to define a scenario pool. You define the parameter space about the scenario pool, and you carry out the scenario simulation with the specific driving function, but on a small scale. For the efficiency aspect, it's better to cover the naturalistic driving testing aspect, which focus on large-scale simulation. To sum up, it's basically about to extend the scenario and investigate your driving function in an extended scenario. So having that in mind, we finalized our target for this analysis. We wanted to cover the safety and efficiency aspect, and study those aspects using the i4Driving model as a human baseline. So how did we do that? For the safety analysis, we focused on selected small-scale scenarios that have been defined in Work Package 6 for investigating safety-critical situations. And on the other hand, for the efficiency aspect, we focused on an extended scenario, on a synthetic scenario for investigating efficiency patterns. For both aspects, the i4Driving model had been used as a baseline for advanced driving technologies. And in that case, we specifically focused on driving technologies based on V2X communication. Maybe I give away in advance the results. We have seen in the analysis, throughout the whole analysis, that the i4Driving model shows heterogeneity, and this underlines the benefit of the i4Driving model since it makes safety and efficiency evaluation more reliable. And I will show you the path how we came to this conclusion of heterogeneity. As a first step, and as Emil already mentioned, one task was to select an appropriate simulation framework. To cover the safety and efficiency aspect, we selected the environment coming from DSpace ASM, which models the ego vehicle in a very great detail. I just will explain it shortly what the architecture behind it is for the ego vehicle. For the ego vehicle, or to control the ego vehicle in the longitudinal way, the ego vehicle needs a reference velocity, which is then transformed to the pedal position and finally is transferred to the vehicle dynamics module. And this is the core of the whole simulation framework, since it simulates a multi-body simulation model with several degrees of freedom. As an output for the longitudinal control, or as an input for the longitudinal control, we get the real vehicle speed based on our reference velocity. On the other hand, since the ego vehicle has to follow the road, we need a reference position, which is the input for the lateral control, which calculates the steering angle again for the complex vehicle dynamics model. So we are able to follow our reference position. We coupled this architecture with Open Traffic Sim, which integrates the i4Driving model with a co-simulation bridge. And I think this is something special because we coupled the i4Driving model with a complex vehicle dynamics model and a closed loop simulation, which you can see here on the right-hand side. So we used the state, which has been calculated by the i4Driving model. We transferred the state with the co-simulation bridge to the ego vehicle, and we fed back the real state based on the vehicle dynamics to the i4Driving model. For the surrounding vehicles, called fellow vehicles, we just mirrored the state calculated by the i4Driving model and transferred it with the co-simulation bridge to DSpace ASM. Having set up the simulation framework, we selected different safety scenarios which capture different interactions. We investigated the pedestrian crossing scenarios Emil already introduced. We selected the car following scenario, and we also investigated the interaction of the ego vehicle with a bicyclist. For each selected scenario, the i4Driving model served as a baseline for the ego vehicle and was controlled by the i4Driving model. As a treatment, we investigated several driving technologies based on vehicle to everything communication. For the first scenario, this was a system based on collective perception. For the second scenario, it was cooperative adaptive cruise control. And for the third scenario, it was advanced braking system directly interacting with the traffic participants. So maybe let's have an exemplary view at the results of one of the scenarios. I picked the car following scenario. As I mentioned here, the i4Driving model saved as a baseline, and the treatment was cooperative adaptive cruise control using the information of the lead vehicle. We selected as safety matrix the time to collision and the minimum distance achieved during approach. And I do not really want to focus on the comparison between the baseline and the treatment, but rather focus on what the i4Driving model showed. Since we simulated the scenario with 3 different drivers, we also have results for 3 different drivers On the left side of the diagram, you see the aggregated results for the baseline, and on the right side, the results for each individual drivers. And what we can see here is, for each safety matrix, we see a clear evidence of heterogeneity of the i4Driving model, since the safety pattern is different for each driver. To cover the efficiency aspect, or in better way, to cover the aspect of traffic and energy efficiency aspect, as a compromise, we selected a synthetic scenario. Here a car following scenario with the lead vehicle carrying out assigned stimuli with different frequency. Again, for the baseline simulation, the i4Driving model was used as a baseline, and for the treatment, we used cooperative adaptive cruise control for the ego vehicle. Maybe a special thing of the scenario was that you see here a mixed traffic situation. The ego vehicle was externally controlled, and in between the blue vehicle, the ego vehicle, and the lead vehicle, we placed i4Driving models, which the ego vehicle has a response to. And as we can see here on the right-hand side, we can see here the results for the efficiency. We selected the RMS value of the acceleration to indicate the acceleration oscillations caused by the ego vehicle. And we selected the mean time gap error, always referenced to a desired time headway of 2 seconds. This was chosen from a perspective of safety and comfort. And again, what we have seen for the safety scenario, we also see here the heterogeneity produced by the i4Driving model. And we also can see here a clear evidence of heterogeneity of the i4Driving model. So to finish the discussion, I finished my part with the slide that I have shown at the beginning. I stated that I wanted to show you that the i4Driving model shows clear heterogeneity, and I hope you could get an insight how this makes safety and efficiency evaluation more reliable. This was it from my side, and then I will hand over to Athina.
Thank you, Christopher. Let me share screen. I'm conscious of the time, so I will be quick so we can have some time also for questions. So this last application is slightly different compared to what the previous speakers presented, because here what we would like, let's say, to assess is how the improved, let's say, human driver i4Driving models that can capture, a better anticipation and perception perform in mixed traffic conditions. So as Emil mentioned earlier, like the i4Driving human factor enhanced models are already embedded in the Aimsun Next simulation software. So for the scope of this analysis, what we compared are maybe 2 scenarios. So the first scenario is the scenario where we just model, let's say, the standard Gibbs car following model in the Aimsun Next software. So before introducing any i4Driving behavioral models, and this is what is considered our baseline. And then we collect simulation outputs related to the traffic network performance, but also trajectory data that were then post-processed in SSAM to extract safety-related indicators. So, and the second scenario was the same analysis, just a second, my cursor doesn't work. But now we have introduced, let's say, in our analysis, the i4Driving behavioral models. So just let's say to give you an idea of why traffic simulation is important, especially in this application. So what we wanted to see is the impact of having more realistic human behavior in mixed traffic conditions and how do vehicles interact with each other. And this eventually can help the way of, let's say, testing ADS in CCAM aligned simulation environments, because traffic simulation environments like Aimsun Next enables us to test, let's say, large scale models with thousands of vehicles interacting, and enables us to derive insights related to the network performance, congestion propagation, but also safety. So let's say the study area that we have selected is the I-80 motorway, freeway in California. So for the simulation analysis, we just considered 30-minute period, and our demand is composed of, let's say, mixed vehicle types that include mainly cars, buses, motorcycles, and trucks. And for the scenario, we have, let's say, performed different experiments with varying penetration rates with respect to the i4Driving, let's say, models. So the 0% scenario corresponds to having no i4Driving models in the fleet, and the 100% we have only, let's say, i4Driving models. We performed different replications, 10 in particular, and the car following parameters, as well as the human factor i4Driving model related parameters, were calibrated against real trajectory data for this freeway stretch. Now, just to give you some insights on the results without necessarily diving deep, we have, let's say, obtained speed headway distributions and then, of course, time to collision distributions from the SSAM analysis. So what we observed is that let's say for the baseline scenario with zero i4Driving models, zero human factors, we have the highest speeds, which is a typical, let's say, human behavior on free flow conditions. Then we observe that in mixed fleet between 20 and 80% i4Driving models, we have gradual speed reduction. So we have more cautious, let's say, human factor vehicles interacting with the baseline human drivers. And then at 100%, let's say, penetration rates of i4Driving models, we observe that the mean speeds increase compared to the 80%, for example, scenario. And this is because we have a more homogeneous, let's say, behavior of only i4Driving models that can restore, let's say, the stability in the flow and have smoother operations. With respect to the headways, again, we see higher variability between the 20 and 80% penetration rate. But as you can see, for the 100%, let's say, scenario, the drivers have more homogeneous, let's say, behavior and show more, let's say, narrower and smaller headways. Now, we have also analyzed the headways depending on some speed, let's say, bands. And I don't want to stay much on this, let's say, results, but just to mention that, again, similarly to the speeds, we observe that the headway variability is higher between, let's say, the 20 and 80%. And of course, in relation to the speeds, we also observe that, let's say, speeds between 60 and 70 kilometers per hour cause larger headways due to probably this, let's say, friction between the different behaviors in the mixed fleet. In this, let's say, the last two slides, I would like to show some results from the SSAM analysis. In particular, here we can see the, let's say, distribution of time to collision across the different scenarios. And as you can see in the baseline where we have 0% i4Driving models, so 0% human factors involved, we have the highest time to collision values that reflect more, larger and more variable spacing, which is a typical, let's say, human behavior. However, in the mixed, let's say, fleet between 20 and 80%, we observe a decrease in the TTC values, and this can be attributed to the interaction and this behavioral friction in the mixed fleet that results to shorter, let's say, gaps between the vehicles. And finally, at the 100% penetration rate, we have the lowest TTC values observed. However, we have more stable, let's say, and harmonized spacing due to the homogeneous behavior. And in the last slide, we can similarly see the box plot and overall trends of the TTC values. And again, we see the shift from the 0% to the 100% with declining TTC values. And I'm conscious of the time, so just to conclude this presentation, so the key remarks is that, okay, traffic simulation at large scale enables us to perform this type of benchmarking and compare like emergent behaviors in fleet with mixed traffic, let's say, conditions. And finally, that the integration of the i4Driving models, in particular in this case, in the Aimsun Next software, and enables, let's say, the assessment of more realistic analysis of heterogeneous road users that can support the deployment of, ADS evaluations for performance and safety. And with that, I believe we can conclude this presentation and open the discussion. Thank you.
Thank you very much for all the speakers. I think this was definitely the one that we had to rush the most because of the many speakers and the many applications to share. There are several questions already in the chat. I don't know if Emil, if you want to go through it or if you want me to go through and pick some of them because the colleagues have been replying to some.
Maybe you can pick the one that were not answered.
Yes, so the first one is, do the i4Driving models have standardized interfaces? Could they be used to replace agents in any other simulation platform without the use of a bridge?
So as we said, the one outcome of our application phase is we have the cost simulation bridge, which enables to link an external simulation environment to the model library. So this is by the cost simulation, but I think the question indicates that can it be natively embedded into the simulation environment? It's feasible. It's just as part of our scope, we didn't deliver any demonstration of how it can be done. Then the model will be open source, so within the GitHub, so it's feasible to take the code and find a way of integrating this in the simulation environment.
So maybe to underline this, the i4Driving model currently is not a standalone version, if this was the question.
Thank you. There was then some exchange about the peers, and the work is still ongoing, and some sharing of the new protocols. Thank you for that. I think this is an example of how these webinars and this exchange of knowledge is useful. Then I'm thinking another question, are the driver models used have deterministic or stochastic behavior? If the second applies, how often did you repeat the simulations to get a meaningful result?
I guess this will depend on the application because each application follow a bit different execution strategy. The i4Driving model has the stochastic behavior elements, so that's one thing. But in terms of number of execution for peers, for example, we execute overall around 65 concrete scenarios, and to as I said, to illustrate the methodology, we just execute one time each concrete scenario.
And for the other applications, maybe you can also share a little bit how it was.
If I may, for the mixed traffic, I already also mentioned it. Due to the stochasticity in the traffic simulators, we performed 10 replications with 10 different random hits per scenario.
Yeah, for our application, we use the WMG simulator. So also one time per concrete scenarios, and the concrete scenarios were quite many, more than 100 for sure.
And ZFs that captured the stochastic element even by applying the different driver characteristics that we have defined within the i4Driving project.
And we still have minutes for. Thank you, Peter, for the questions. We still have 1 more minute. We are 1 minute after, but I will give 1 more minute to our speakers. I think we can extend the lunch break a minute or two. See some, maybe in the meantime, any recommendations for future work? After i4Driving, what else? What were we missing? What we didn't have the time to continue?
I think just to comment based on what I said, the time was quite limited in making those applications, and as I said, the findings are more about demonstration that it is feasible, but we can't make any safety conclusion from those results. So I would recommend to follow the similar path to make those simulation on scale, and to follow the complete workflow of the evaluation framework, and to showcase the some safety conclusion based on scale execution.
Then I think, well, once again, we have to wrap it up. It was quite a lot of information. The webinar will be recorded and published in YouTube, and it will also be available in the i4Driving website. All the deliverables will also be published there. We are still finalizing some of them because our final deadline is the 31st of March. So in this case, you are actually hearing some of the results before we even publish the report, which is on the going. So thank you again to our speakers, and also thank you for the participants for having joining us. And there's one last webinar on the 31st of March with some of the final results and some recommendations for policy and industry. So please join us as well. And have a nice afternoon.
Thank you very much all for joining.
Thanks, everyone.
Thanks, everyone.
Bye.